Okay, I lost track of what I was looking at on my picture. This really is the y-axis because we're looking from the positive x-axis, and obviously if we look along here from the positive x-axis, we're going to see the circle and we're going to see the y-axis moving off to our right. So some of the stuff I said before is just not valid. So I'm kind of tempted to go back and start the discussion over, but I think some of this stuff was explained in a way that I don't want to try to repeat. So let's just go back to my correction. This really is the y-axis, and the distance from here to here is the distance along the y, and of course that distance is going to be y star, and this distance is going to be 4, and this distance is going to be the radius of the circle that we get here. Okay, because when we're looking face on, we have a green, it might be hard to tell yellow from green, colors don't contrast as well, a green line that could go all the way through here, indicating the edge of this plane y equals y star. And then we have this yellow segment of that line that I've recolored as yellow, that corresponds to our edge view of this circle. Now I've drawn it all the way from here to here, so it's really an edge view of the entire circle. So you're looking edge on at a circle, and then clearly from here to here will be the diameter of the circle, from here to here will be the radius. So this blue segment now is going to indicate the radius of the circle, and by this triangle, where we know that we're at distance y star along the y-axis, and the radius of the circle is 4, that distance has to be this leg of a triangle with legs y star and hypotenuse 4. And that's going to be, of course, 16 square root of 16 minus y star squared. Okay, so that's the radius of the circle we get when we cut this plane. Now you don't actually have to know that in order to answer the immediate question, but it is something you're going to have to know to set up the limits on an integral over this sphere. So we mention it now. And also, this is mentioned just to orient you to what this picture is telling us. Now the question really is then, if we confine ourselves to this plane, we have this circle. Now this circle is not this circle. This circle represents the intersection of the YZ plane with the entire sphere. It has radius 4. This circle is somewhat smaller. We want to know above the point x star y star what the slope of that curve is. The slope of this circle above the point x star y star. Okay, and we don't have a picture of that, but what we have to understand, and what people had a hard time with, is simply what we really ought to understand from our previous chapter, that the slope is in the direction of this plane parallel to the YZ plane. It's x that's changing in that plane, so that the slope at this point is the partial derivative of our z function with respect to x. Okay? Now, we don't have a z function. We haven't really talked about our z function, but our z function has to obey x squared plus y squared plus z squared equals 4. So whatever our z of xy function is, and z of xy would be the function whose graph is the sphere, we would take the partial derivative of that function with respect to x at the point x star y star, and that would give us the slope of this tangent line. And then we would use the slope of that tangent line to find a vector tangent to this point on the surface of the sphere above the x star y star point. Okay? If we move in this direction. Okay, well, we're going to talk about that in the next clip, we're going to actually get the expression for that vector and for that slope.